From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. Our guest today is Dr. Wei Li, Intel's Vice President and General Manager for Artificial Intelligence and Analytics at Intel. Working as a technologist and leader with Intel for more than 20 years, Wei has always been at the cutting edge of Intel's hardware and software advances. Wei and his team's goal is to improve the life of every person on the planet through increased computing performance and human productivity. This podcast is sponsored by Mouser Electronics, a global authorized distributor offering the world's widest selection of the newest semiconductors and electronic components. Wei, thanks for being here today.
Hey, thank you. I'm glad to be here.
So, what is your origin story? How did you get into engineering and technology?
We all go back to our roots, mainly our high school days. And I was pretty nerdy and was very interested in math specifically, and enjoy geometry, enjoyed algebra, and on the geometry side, I like plain geometry. Something very simple, but it's very hard. It's very hard to prove these things, even they can be described in a very simple way. And I like algebra, and intrigued by things like matrix algebra. How can you represent things in matrices? These are all fun things, and I really enjoy these. And eventually got into interesting computing, and that seems to be the natural evolution from math to computing here.
So, do you remember maybe some of the early? Our audience loves to geek out on some of the OG computers. Do you remember the first computers you worked on? What they were?
Yeah, I think my first computer, I guess maybe I'm aging myself here. My first computer was a IBM PC, and it's I think I probably learned BASIC and then Pascal, and got a chance to write programs in these.
So did you know at that point computing was for you, and what did you do for school after that?
Yeah, so I believe computing is the sort of sweet spot for me. I was very interested in math, but I want to do something useful. Nothing against my mathematician friends. I want to something more applied, something that can actually have a real impact, something I can feel, I can see. So I got into, I believe computer, looking back, is the right choice for me.
We won't tell the mathematician folks. We're all engineers here.
Hey, many of my math friends who got PhD in math, they end up, either on the high tech company or Wall Street somewhere. Very few of them actually end up doing pure math.
Sure. And then you got a PhD at Cornell in computer science. Can you tell me what you were studying and researching there?
Yeah, so I it's interesting because one of the earliest programs I wrote was actually matrix multiplier, because I was very intrigued by how you can just write 3 loops and then all of a sudden it will do the multiplication for you, right? You don't have to write down all these numbers and it just happen automatically. So that's pretty fun. And then when I got to Cornell, and I got interested in supercomputers. At that time, supercomputer was very hot as a research area. There was funding from NSF, DARPA or ARPA, all these different places. So what I ended up doing was using matrix algebra for matrix applications. So I was talking to my son a few days ago. He said, "Yo, you got stuck in the matrix ever since." So it was. So I just happened. I guess that's my fate. Happened to be somehow related to matrix and matrices. And so my thesis was actually a parallelizing compiler for supercomputers, for parallel machines. And you can imagine on the parallel computer side, supercomputer side, people run a lot of simulations on top of this, right? You're talking about simulation, and the simulation tend to be eventually, at the bottom line is going to be PDE, is going to be matrices, because it's all solving matrix problems, right? Solving matrix multiplication, LU decomposition, QR decomposition, factorization, all that stuff you guys are familiar with on the EE side, right? Now the unique thing is, I'm building a compiler try to speed up these things. And so inside the compiler, we want to automate the the process of optimization. So you want to transform a program from, you write program in C, C++, and they transform to something else, which is faster on the supercomputer, right? And the transformation I create a framework using linear algebra. So my framework is actually, it's a linear framework for representing all these loops. And then you can think of vector space transforming from one vector space to another vector space. You can imagine it's a linear function, and it can represent in matrices. So there's a lot of matrices, because I just deriving all these matrices to figure out transformations for better performance for these applications with matrices inside. So it's been fun.
You're giving me flashbacks to my linear algebra class in college. I can just see the whiteboard and all the matrices. What is your philosophy on compilers? They're such an interesting combination of like inputs into hardware. Can you talk about that?
Actually, I like compiler. That was my roots, and I like, because it has both. As I mentioned to you, I like math and I like the practical side of it. So compiler allows me to do software still with a very strong mathematical foundation inside, and then compiler can do both things. One is performance, the other is productivity, right? Because I keep going back in my career, I think about what have I done? Really, it's performance and productivity. So productivity, some people may not realize. The reason we built compiler was, in the old days, people wrote assembly code in order to get work done, right? And from assembly code to a high-level language, that's where compiler provides you the opportunity for doing this, right? So it is up-leveling things, and we continue to up-level, to make it easy for people to get their work done. And then on the other part of this is performance. So all my life, it's all about getting things done fast, right? So you not only getting things done fast, but also getting things done in the efficient way, right? In a way that automation, compiler really is about automation. Is about automating the process of optimizations for other people. And I imagine it has done the job. It's helped a lot in the computer industry for the software side. Even though I still ran into not very little nowadays, but more than 10, 20 years ago, I still ran into people who really like assembly code programming. They will never use high-level language. These are the people I really enjoy talking to. The guy is just actually, to be fair, a portion of my team is still also on the assembly language side, because that's how they squeeze the last ounce of performance. These are the library developers. So I have a library called 1DNN library for the neural network primitives. And over there, because it's so central to everything we do, and performance-wise, you want to get the convolution primitive right, and the way you do this, you really want to count the cycles, and this is how you end up in the assembly code land. They want to have complete control of register allocation. They don't trust the compiler doing register allocations for them, even though there's so many papers published on the register allocation side over 20 some years, right?
Yeah, I feel like those people dream in hexadecimal.
Yeah. So these are the people. I think these are the fun people. I got a chance to interact with.
In working with supercomputers, do you have any moments of where you felt like you were a genius, or you maybe had a moment of, I might have just broken this really nice supercomputer? Do you have any moments like that?
Yeah, I have moments where I think there's mixed emotions. In some days, I feel like, wow, it's great, and I can do all these big things with these supercomputers, right? And then in some moments, when I dig deeper into it, you look at, it's pretty fragile also. Pretty fragile, because you think about, even at that time, we're talking about more than 100 nodes. It's pretty big already, and but things just not working as a low-level compiler person, developer for, like what I did, right? It was not easy actually to get the best performance out of these machines. It's more than just you have more nodes. So it's more than just more CPUs. All of a sudden everything's cool, because you have to orchestrate the data movement, in an efficient way. That's really the tough part. It's still tough part today. Actually, it's more interesting today when I work on AI nowadays. And for AI, particularly deep learning, eventually it is still matrices. Actually, deep learning comes down to, at the end, is still convolution, matrix operations, and how do you do this in a massive parallel machine? Because every AI accelerator is a massively parallel machine. So it is anyway, but it makes it fun.
Yeah. And then you've spent the last 25 years working at Intel. Can you tell me how you've seen technology evolve and adapt over time?
Yeah, so I'm fortunate, because to be able to work in the company. We're always at the cutting edge of the company. That makes my life exciting. And when I joined Intel, Intel was going through transformation. Intel was growing, and Intel wanted to grow from a PC company alone to a server company. Server was just coming out, and all that. And the reason they hired me, they recruited me, was they were building a 64-bit processor. And it was a big deal because the PC was a 32-bit machine. They wanted to go to 64-bit, and Intel was trying a variety of hardware options, and they all wanted to have a compiler to build on top of this. So in that experience, I had a chance to see how we can transform ourselves to go to the adjacencies to be very successful. Intel today is very successful on the server side, and so we got into the data center, eventually became cloud, and so for us, we got a chance to look at different kinds of workloads. Some of these are very compute intensive workloads. Some of these are very data intensive workloads, right? So the applications we're optimizing, things like I'm sure your audience will know things like Nastran, ANSYS, right? These are the software area a lot of people are using. And then these are the compute intensive side of it. And on the data side, it would be things like Oracle or SAP, SAS. These are enterprise applications with a lot of data inside. So we got a chance to see how these applications work, and then actually help us to design both software and hardware, because Intel is mainly a platform company. We provide these platforms for people to develop applications. So also understanding these applications is pretty valuable.
So I've heard, when I think of Intel and I see the Intel Inside sticker on my computers, I think a lot of people think of Intel as like a hardware and a processor company. Is that still fair to think of Intel that way, or how should people reframe their thinking?
Yeah, in Intel, it is still a hardware company. We still make a lot of money. We I think last time we checked, is many billions of dollars every year. We make money out of hardware. But Intel has changed quite a bit in my career, more than 20 years at Intel. We have been evolving to become I think today we're calling it software first for Intel. But just to be fair, we're not quite there yet. We have a vision to be software first. But I think today I'm very glad to see we have evolved into somewhere in the sense of software plus hardware as a company. And I think it's a good change for a variety of reasons. For a good reason for our hardware products. It's also a good reason for our developers, because eventually, good for the software for develop for our customers. Intel has become a software plus hardware company here.
And you've won several Intel Achievement Awards. Can you tell me about some of those moments in your career where you were recognized and your teams were recognized for having a big breakthrough or technology?
Yeah. So that was a fun experience. So the first time I won the award, I didn't realize it was Intel Achievement Award is the top award for Intel, and it's like winning an Oscar. And so the award ceremony is also like winning an Oscar. It's like Oscar ceremony. Actually, the my first one to remember, we had this ceremony in the one of the nice hotels in Coronado Island in San Diego. You may recognize it's a red color and on the beach. It's very, very, very nice. And one of the recent ones I went to was in the theater in San Francisco. So people actually dressed up. And we're all engineers, right? Usually
Yeah.
t-shirt and all these things. And then when you go to these events, like tuxedo, some people would wear tuxedos and all that. And then you have to go up on stage, give an acceptance speech, right? So I used to watch Oscar, not anymore. I don't watch TV anymore, but used to watch Oscar. It was fun. It's a very special moment. I'm glad a lot of people. It's very selective. Only a few will get it every year, and I'm glad many from my team able to achieve that.
And your last couple were for AI ML related technologies. Can you tell me kind of what those were for and what you've been working on lately?
Yeah. So I think the last two represents the kind of work we do in the past 6-7 years or so on the AI side. The last one was on the co-design, on the software hardware co-design. So we actually added hardware acceleration inside CPU for deep learning. It's for deep learning specifically, because you usually think about CPU as a general purpose thing which will run anything you want, but we actually deep learning was so important, so we added something called DL Boost VNNI. It's a vector neural network instruction. This allows you to run integer 8 operations, vector integer 8 operations. So for those of you who follow deep learning, because eventually when you do, particularly do deep learning inference, if you can do it inside 8-bit versus 32-bit, that will make things run faster and so on. So that was pretty cool for our team to win that. Now the previous one, the year before that, we actually won this for the software work we did. So our initially the AI software on Intel platform, particularly on the Xeon side, was not really well optimized, and we left a lot of room in terms of performance. So we came in, we optimized the software, we speed up performance by 200x. Who could have thought you could do the like 200x, right? Because I've been working on the stuff for years now. I still find hard to believe. It's like you have a software can make such a difference, because even when people deliver products, if they can do 2x, is already a big deal. You quite often they can, I improve my performance by 20%, therefore you want to buy my stuff. But this is just incredible. So
it's a whole different ballpark.
Yeah. That's the beauty of deep learning. So actually, same thing for machine learning as well. We've been able to see very, very large performance differences through software optimizations.
That's incredible. So historically, I think of hardware coming out, and then the software people they take the hardware and they try to just get the most out of the hardware they can. You mentioned co-design. Can you talk about what it takes to have the software folks and the hardware folks work together to make something that's greater than how it used to be done?
Yeah, so these are the changes we have seen at Intel over the years, and even today within my team. So my team, for the most part, is software. So majority of my team is working on AI analytics software, but I do have a portion of a team working with hardware architects very closely. Their job is to co-design our hardware features for AI, and that has been pretty interesting, because we're changing the process, changing the philosophy of designing our hardware as well. And we really want to use the workloads. I mentioned workloads before. We want to understand the workloads, because eventually you want to run these workloads fast. So we want to have a deep understanding of these workloads, and that will drive the new features inside the hardware. And it's pretty it's different from building software products, right? Because on the co-design side, you first need to understand how well it is doing today, and you find out, here are the bottlenecks, right? Some of these bottlenecks you can address it using software techniques. And some of these bottlenecks, you probably want to have hardware acceleration. So I'm telling my hardware friends, I want to think about differently. I want to think of, the hardware guys are serving us, right? I mean, they are just hardware, just acceleration for software. It's not the other way around. It's not software is enabling hardware. Hardware is just an accelerator for software, right? So the things we cannot do in software, we want help from the hardware side to change things. And then quite often we identify these things, and then on the software, on the early design, it's we have to work with simulators and all these things, and we have different kinds of simulation environment we do, and some of these are functional in nature, some of these are performance in nature, cycle accurate, and all these things, traces, and so we end up, we have to prove why these things can add performance and improve the overall capability, and then eventually you design new features. So it's becoming more of a co-design today, which I think is a good thing. It's a good thing on for the hardware side also.
The software team has to come at it from, here are the features we want, and here's the hardware we need to enable these features. Is that how?
Yeah. So in reality, it's a collaboration, right? It's a tight collaboration. So my team actually sit next to the hardware people together, and quite often people cannot tell the difference which organization they belong to, because eventually it doesn't matter which org you belong to, right? So quite often people say, hey, these two people, they came up with this thing, and it happened to be one person's from my team and the other person's from the hardware engineering team. So it worked out very very nicely.
Fascinating. Yeah. On the heterogeneous computing front, are you looking at more than just CPUs? Are you doing GPUs and TPU type architecture?
Yeah. We are doing we're doing multiple things. Even what I do within my team, we're looking at a CPU and a GPU, and so it is. And Intel overall, you may be aware, we acquired a AI accelerator company, Habana, recently, maybe about a year or two ago. And so in terms of Intel, we cover multiple pieces: CPU, GPU, and the special AI accelerators. And I think the future is going to be heterogeneous, because it's not going to be one size fits all, and particularly when AI is changing very rapidly, and the different workloads demanding different kinds of solutions, and so there will be very it's a very different kinds of varieties actually. And this is a heterogeneous could mean inside CPU you add more things to it, and you can be things outside CPU. It can be a GPU. It can be the various different kinds of integration, and some things should be integrated. Something should be discrete, should be separate.
How do you decide?
It's also workload driven, right? It's workload driven to see. So we're tracking the not only today's workloads in AI, but also tomorrow's workloads to see. And that's why I very, I came out of more of a research background myself, and I'm still very much excited to talk to my research friends, people in universities. I still work with them actually, some of them very closely, and I really want to track what's going on in the cutting edge, the real cutting edge, not only the cutting edge in the field, right? And see how things are going, and they'll help us figure out what is the right software and also what is the right hardware solutions for these.
Can you tell me a little more about what you're working on? Maybe some upcoming projects or products you have. Obviously nothing that's not public, but I understand there are a couple of things you can talk about that are in maybe the near future.
Yeah, so there are two things in the near future that we're working on. One is we have a software sitting on top of the CPU called Sapphire Rapids, and the Sapphire Rapids will have a lot more acceleration for deep learning specifically. So we're actually putting in a matrix unit inside. We cannot get away from matrices here. We're putting in a matrix unit inside the CPU. And this is going to be a game changer for deep learning. And you just imagine you are embedding you integrate a GPU inside the CPU, right? So that's very exciting. We'll see very, very meaningful performance differences in terms of solving the problems people have on both the inference side and the training side and all these. So that's a pretty exciting piece. And then the other exciting piece is GPU. So we also have the data center GPU coming out under the new data center GPU, and that one has even more. In terms of compute capabilities. So if you count the number of flops, it's going to be a huge number, right? And not only that, but we also have been working with Argonne National Labs. You're talking about research, talking about connecting to the people on the cutting edge of these applications. So we're building a exaflop machine, a supercomputer, the still supercomputer at the Argonne National Labs, and they will be looking at running a lot of large applications on top of this. So this is another. So I think I'm looking at two sides of it. One is the CPU play will give us sort of broad, right? CPU is everywhere. Particular. I mean, our Xeon is every data center has Xeon, every cloud has Xeon. It's just everywhere, right? And our GPU can go to very top in terms of supercomputers and all that. So it gave me I enjoy the playground. It's an interesting playground to all the variety of things over here.
So GPUs in a data center, are they doing this machine learning, machine model training sort of things, or why are GPUs so important for the data center?
Yeah. So GPU can do both training and inference, and particularly on the training side, because training as a particular deep learning training as a workload depends on how you use this. So certain workloads are very, very demanding, right? Because you go to one end of it. Let's say some of these NLP, natural language processing workloads, and these models have become humongous, right? And they reach like a trillion. You can imagine like a trillion parameters, right? And these are at least many billions, right? Hundreds billion all this. So these are very big. In order to run these things, you do need a lot of compute. You need a lot of compute. You need a lot of not only one GPU is not sufficient either. You need multiple GPUs to do these things. So there's a need for large amount of compute, and I think GPU is a pretty good solution for many of these.
Yeah. So you mentioned that you can't get away from the Matrix. Did people's perception of your work change after the Matrix movie came out? Like, it kind of added this cool connotation to a fairly rigorous math concept.
Yeah, I think I watched the movie of Matrix many years. The first one came out, I think more than 20 years ago. So I didn't pay that much attention until recently. Sort of remind me the Matrix is actually very cool because a lot of stuff. I don't know whether the producer or director they foresaw this or not, right? Because it's ironically today the foundational AI, particularly deep learning, is matrix actually, and then a lot of work we do is simulation, right? So it so maybe they predicted. I don't know, but
it could be true. It's what you're saying.
It could be true. Say, hey, you're not talking here. I don't know whether we are real or not.
Fair enough. So talking about AI and machine learning, it seems like they've just taken over the world by storm. What are some of the challenges that are remaining for AI to truly be effective and usable in the real world?
Yeah, so we have seen a lot of AI applications already, but also there's research that shows 80% of AI ideas never made it to reality. And the way I think about this is AI today, for the most part, initially at least, it was done by in the research environment, in the lab environment, and it was done by smart people working on PhDs for neural networks, right? And so it's a very narrow environment to begin with. Now, once you go broad, you want to go to everybody using AI everywhere, and you run into real world issues, right? So I would say two real world issues here. One is the real world is more complex than the research environment, right? So if you recognize cats and dogs, what you need is a bunch of images in JPEG file somewhere here or there, and that's your starting point. That's good enough. But in a real production environment, your data is all kinds of messy places, different kind of databases and all that. That's the thing we are learning within Intel also. We go to our manufacturing environment. We do have a lot of data, but the data is not just some simple pictures of that dog and cats. The data is quite messy, right? And so to go from that kind of data to insight, it's not easy because eventually the solution is you want to go. The problem really is you want to go from data to insights quickly, and that's not straightforward. And then the other is the skill set, right? Even skill set, the people you run into, they're not PhDs working on deep learning, right? I mean, they're smart people, but not PhD in deep learning, right? So they may not even know. They never learn, SQL, even process data to begin with, right? And they never heard of. They may learn linear algebra in high school, but they never made a connection between that to what's inside deep learning. So it's a skill set is also different. And I think these are two major reasons. And the complexity, the end-to-end is very complex. You go from data, you have to go through multiple stages before you get to the model, get to deployment. So it's not a simple problem to solve here, to go broad.
Yeah, I almost see like two different camps of AI. One is bigger, more complex models running in cloud systems, but then I also see like tiny ML where people are running microchip based models on small little edge compute boards. Can you talk about is that fair to kind of differentiate the two and maybe how they're different or the same?
Yeah. I think it's fair to differentiate these two here. On one hand, you continue to push, the bigger, the better kind of thing. If you look at GPT-3 and all that, and actually at the beginning, I thought this was just a research, it's a research marketing thing, like you get the largest possible. But in reality, when I talk to some big cloud service providers, they do bring value. These huge models, they actually even when you try to train these models, it's not cheap, millions of dollars to train these models, but people still find cost effective to do these things, to provide value on the cloud service side. So there's value for these huge models, but on the other hand, there's the small tiny thing you mentioned, and that these things going to be everywhere, right? I mean, it's like a little bit scary to think someday, my entire home is going to be all wired in some way. And so another kind of thing we've been looking at is how do you start with a big model and then you distill it and then come up with a smaller model to meet your need, and the model is the same accuracy, or at least without loss of too much accuracy, and give you a small model more efficient that way. So that's another sort of AI thing we're doing here. It's pretty exciting.
Yeah. What makes it cost $1 million to train a big model? Is that just energy and compute power?
It's just basic compute power, and the amount of computation you need. It's just amount of floating point computation you need to do this, and and amount of bandwidth you need to do. I mean, amount of data movement you need. The amount of data is pretty large.
Okay, that makes sense. Can you explain where do you think AI will be in 10 years, in 20 years, maybe in 100 years? Kind of what's your vision for AI everywhere?
Yeah, so I think at the top level, the AI, I've been a proponent of advocate of AI everywhere, and I think today it's probably not a controversial statement, and AI, many of us believe AI will be everywhere, and I would just say I think top level thing is we contribute in some positive, meaningful way. I mean, it will be improve the life of everyone on the planet, right? It's a positive change out of all the technologies we're building here. So that's at the top level to make it more meaningful. And then when you go a level below that, I would just say a lot of things would be AI driven, so we're seeing that change already, and over time. anything you can imagine, really anything you can imagine, we can use AI for. Uh,
Sounds good. Sign me up
and
for
I
sure.
wouldn't want to predict what's going to happen in 100 years, because given the AI change in the past 10 years, you can see a lot of the stuff is not predictable, right? It's like we've been in this benchmarking business for a long time. Try to say, oh, these are the standard benchmarks you want to uh, measure your performance, for the products you're developing. And some of these applications been around for a long time, but AI is really changing very quickly. Like something like BERT, it came out only a couple of years ago. The second year, it became one of the standard benchmarks people want to measure performance on. And next year would be something completely different. Now transformer and all these things. So it's hard to predict.
What sort of parameters do you use to benchmark an AI? Is it accuracy or speed, or does it just really depend on the system?
Um, Depends on what you want to do here. Usually, you have a accuracy. So this is sort of standard state of the art accuracy you have to achieve in order to be real, right? Because you can always run fast and always wrong. That's not very useful here, right? So you have to be correct first. So you have to meet certain accuracy. So once you have met certain accuracy, then you need to measure performance in some way. And usually performance is measured by two aspects of it. Depends on the usage model, because some of these usage models tend to be throughput oriented. Like in a data center, you want to serve. I mean, you have probably millions of audiences and people listening to you, and you want to how do you serve million people at the same time? So there's a throughput environment to it, right? And then the other aspect is the latency, because you have to have minimum latency. You cannot say I can process million of these, but everyone will take an hour to come back. That's not going to be useful here, right? So there's a latency environment. So we actually benchmark on both sides for the products we're building here.
Okay, that makes sense. Um, so what is Intel doing? What are you doing at Intel to make Intel the go-to company to take on the AI problem?
Yeah. So what we're doing here is, I mean, AI first of all is opportunity, is also a problem, right? It's an opportunity because its growth potential is huge. It's also a problem because we're not there yet. So these are problems we're trying to solve here. And luckily for Intel, we are a hardware plus software company, right? As I mentioned earlier. So we actually have we can do a portfolio play here, and Intel is pretty unique because we're big, right? We're big, and we have scale. So the game really is scale game. For AI to be everywhere, we have to have a scale. It's not a. This is fortunately a big company advantage. We're a big company disadvantage also, obviously, but the big company advantage is we do have the scale, and particularly for Intel, we have both hardware and software. And on the hardware side, we can have we have a portfolio of variety of solutions. So the heterogeneous set of things. We go all the way from CPU, GPU, spectral accelerator, and even FPGA, and so we have all of these actually. Now, once you have all of these, it's the other is challenging part is how do you make it easy for people to use these things, right? So the other way we're doing is software. Can software provide a productivity play in terms of make it easy for people, and performance play obviously to get the best out of software hardware. And the other thing on top of this is, can software unify the heterogeneity from it, right? So there's a performance gain out of heterogeneity, but heterogeneity also makes it hard for people to use it, right? And so what you don't want to do is you want to write a program, and today you say, oh, my program will work for one CPU plus two GPU, and tomorrow all of a sudden it's going to be one GPU, three CPU or something, right? So things can change, and your program should move more seamlessly, right? So we need to provide the environment where we have different level of abstraction. So whatever happens underneath should be invisible as much as possible, and you get the benefit without incurring the cost of people having to manage the complexity here. So that I think these are the things we are doing in the company in terms of both software and hardware to eventually make it easy for people to get the benefit without having to suffer the pay the cost of doing this.
Yeah, I'm all for, like we're using computers now. We're not thinking about the assembly language running on the processors to make it working, but we're still able to use it seamlessly. So that level of abstraction seems pretty important to make it widespread and usable.
Yeah, that's required to be widespread, right? Because you can't require everybody to be a deep computer scientist to use the stuff, right?
Yeah, I don't want to have to choose how many neurons I'm using for my model or necessarily even what algorithm. I just want to be able to say, here's my image set, make it so, right?
Exactly. You just have the data. All you want is I have the data. I want to get an answer from whatever answer you're looking for, right? So it will be it won't be good if we force you to figure out this is the neuron you want to fix. This is the matrix you want to do, or this is the link you want to cut, and that these are all messy stuff, and leave it to others to work on that stuff. But you're creating jobs for humans, so that's good.
Yeah, absolutely. You've been a pretty vocal proponent of having a fairly open AI ecosystem. Can you talk about how much insight we should be giving people into it, and how much abstraction is maybe too much?
Yeah. So I think that there are multiple levels here. So first of all, I think the open ecosystem is critical for businesses and critical for society also, right? So it's a good thing in general for everyone involved here. And one of the key benefits we see, even as an enterprise, an open ecosystem is a place for innovation. It really can allow people, innovate. The speed of adopting the innovation is also much faster. You don't have to wait for some company to sit on it, and so it is much faster to get new stuff out in the open ecosystem. So that's a great thing here. And then the other thing is the adoption is a benefit, right? It's adoption is another benefit because it does have the economy of scale. Because a lot of people are involved in this, they're contributing to it, and for us to get our ideas out, to get to the ecosystem, there's a fast way of getting there adopted for adoption as well. And it's in general is a level playing field, right? It's a choice. People have a choice. You're not constraining them to be in a particular thing because it's open. Not only you can use it, but quite often you can contribute to also. So you're not get stuck somewhere. You're not get stuck in the matrix in that sense. You're actually free to choose different things because they're open here. So there are many different good reasons for this.
Yeah. What does openness look like in this case? Is it access to code, or kind of what does that mean?
Yeah. So openness, I think it will be multiple aspects to this. One is access to the code. You can use it, download it, and the other you can change it. You can change in different ways, right? Because you can change it, the implementation for a particular spec, and you also have a voice in terms of changing the spec itself also, right? So let's say if you have an open programming language, and you have a voice there, whether the language should have certain features or not, right? And you also have a choice to implement the language on the platform you are developing. Let's say if I'm a startup doing AI startup, I build this next generation AI accelerator, which I think is going to be wiping out everybody else, is the best ever existed, right? And then you want to have a software stack on top of this. So if you have a language you can implement on top of your hardware, that's a good thing for you, right? Instead of a language you cannot do anything about it. So that's this openness in a variety of ways here.
So what is Intel doing to encourage this openness? Are there resources available if I wanted to go get started with it?
Yeah, so Intel is pushing pretty hard in both directions. One is openness, the other is make it easy. So actually three things. There's a performance side, naturally, we've been doing forever, and there's a productivity side, and there's an openness side. right? And one good example we have here is most recently, working with our partner, our collaborator, Accenture. Um, we just launched a set of things called AI reference kits, and the reference kits are designed to be open. It's open source, and also designed to be make it easy for people to come up with solutions. So that's the one step for us to move in that direction. When we talk about AI everywhere, and we want to make it easy for people to develop AI solutions. So the reference kits are in that direction.
So what is in a reference kit? What do I get if I have one?
Yeah, so the reference kit. So the first set we launched, we had four in them, and over the next couple of months or so, we were going to be doing much more. We're still rolling out in the phased approach. And if you look at the reference kit over there, so they were designed to for particular use cases. Maybe in different industries, so you want to be close to the problem people have. Let's say one example of that is, we have a reference kit for chatbot. And if you want to build a chatbot, you already have a good starting point. So now inside the reference kit, we provide the code, the Python code for the reference for chatbot, and we provided a model. In this case, a BERT model inside a deep learning model inside the reference kit, and we also provide the reference data set, access to reference data set, so you can actually try to train the model using the reference data set. And we also provide documentations to describe the overall architecture and all these things. Now, on top of all of these, this is sort of get you started. Now, on top of this, you get all the optimized software we've been working on forever, right? The software we talked about earlier, things that give you 10x better performance, 100x performance, and these software is actually inside these reference kit. So once you either use a reference kit or use it as a starting point, modify whatever you want, right? Because it's open source. If you have your own data set, you can train it on top of this, right? You can do all these things, and the end result is you can actually have a faster solution, so you can save your cost. So if you go to a model, the model can respond more quickly. Then it's good for your customer already, because nowadays, chatbot is everywhere, right? So sometimes the chatbot response is slow. You don't want the customer to be waiting there for the response to come out, right?
The little
So
dot
if
of
you
it typing.
it's like, oh, please wait, I'm still thinking, right?
Yeah.
So you want the response time to be fast, latency. You want to be able to serve multiple, many customers at the same time. So performance does matter in these things, and so both in this good example, both productivity and the performance to have a better user experience and hopefully save your money also. If you are doing this on the cloud service provider, you want to pay them less, right? To serve your customers. So it's just one example. We have other reference kits in terms of another example I'll give is like a quality inspection. So, like if you have a scratch somewhere, as you want to develop something to automatically recognize scratch and all these things. So there's a variety of things we're looking at. So in general, we want to get to closer to the user, to the customer, to the developer, where you can actually either make this as a good starting point. If you haven't done anything yet, this could be a good starting point. But sometimes people already have a machine learning solution, right? If you have a machine learning solution, you can still use a reference kit as a reference, right? Because if you have maybe, let's say, if you have a machine learning reference kit and you want to think about deep learning, you can say, hey, how do I use deep learning for this thing here, right? And even you already have deep learning, for example, then you may be using some old software, is not performing very well, and you just upgrade to the optimized software. It gives you the much better performance, and you can save money, get better user experience, and all these things. So it's useful for multiple layers, different types of usage models also.
Okay. It's almost like, if I'm trying to get a chip implemented on a board, often there's a reference design for it of all, put some capacitors here, that sort of thing. It almost sounds like it's that, but for software.
Yeah, exactly. And I think that's useful when you go broad, right? When you go broad,
Yeah.
for this.
Excellent. Are there any companies or any Intel customers that you see are doing some really interesting or unique things with AI ML that maybe surprised you and the rest of the folks?
So there's a lot of interesting stuff going on, and particularly I go to research conferences a lot and look at Neurops and all these places, ICLA and all that, and just see what it's amazing. A lot of stuff going on, right? Because people trying very different things here or there. So I would say maybe I'm spoiled a little bit because I'm deeply inside AI and then look at all these things. It doesn't surprise me as much as before because I look and say, yeah, I can imagine this. I can put myself in the shoes. I can say, yeah, I can imagine if I put a few smart graduate students here, we can actually get this thing done, right? That's possible.
Yeah.
And the thing is even still today, sort of I was surprised, not didn't expect was a couple of years ago actually. DeepMind, they had AlphaGo. You actually beating the Go champions, and I didn't think it would happen so quickly because I'm not a Go player because I only play bridge and all that. Go is more complex for me because I have friends who play Go. I mean, these are multi-hour games and it's more complex. But even in that environment, the machine basically not only won the first thing against some world champion, but after that, but the machine was consistent, right?
Yeah.
It's not a one-time deal. Now
Wasn't
human just give up. It's like you cannot fight the machine anymore, right? So that's amazing.
Yeah. Yeah, it's a little different than bridge, I think.
Yeah, it's different in terms of the number of options is much bigger, right? The combination is much bigger.
So for our lightning round, are there any situations in pop culture? You said you don't watch TV, but you've seen The Matrix. I assume you either read or something. Are there any pop culture moments that really get AI right or really just get it wrong, and you watch it and go, ooh?
Well, there's a lot of hype on AI, and I sometimes watch YouTube, and we talk about people, the robots behaving in certain way, and I see two extremes. Sometimes people too hyped on AI say, hey, the robot is going to wipe us out, control entire humanity. And sometimes people say, oh, the robots are dumb. They can't, they all make fun of robots. But the reality is in between. Actually, we can, do a lot with the AI, even though they're not quite as smart as human yet. But in some aspects, they're already better than humans. So we have to accept that reality.
Fair enough. Yeah. So I've heard that you call your engineering team magicians. Can you explain why?
That's a great one. So part of the reason I enjoy the work is we have the great people to work with, and I call them magician because they can do two things. One is they're very innovative. They can innovate and deliver, and that's a combination I like. That's a combination. Not everyone has that combination. You can see innovative people who never get anything done. you can see people who busy working on stuff, but they don't know how to innovate. So I really enjoy that combination. That's why I call them magicians. There's a longer story about the magician side because we had a project before, and the project was so unexpected, and the CEO at that time said, "Oh, you better have a magician name," because at the beginning I use a name from I live not far away from San Francisco. I use a name called Stern Grove. I said, oh, that's a nice place. But then he said, no, that's a boring name. You have a magician name. So we eventually came up with a magician name, and that got stuck. So it's good. The way I think about it is I couldn't use any virtual background for this chat. Usually I have a magician background. Virtual background.
That's awesome. Best and worst project names you've ever heard?
Oh, best or worst project names. I don't pay too much attention. So I think I've seen more worse project names because our loyal friends were within the company where they have a limit on what kind of name you can choose for project names, and they all once you've done a few of them, it all become repetitive or become very boring. But I wish we could be more creative to do any project names we want. So
Just some guidelines.
Yeah.
I've heard some stories of people using like Marvel characters for project names, and then somehow it leaks out and everyone gets in big trouble. So I understand that.
So there's a reason for these guidelines, I guess.
Yeah. Yeah, I've seen a bit of that. That's probably all I can say about that. What skills would you recommend for engineers who are either still in school or they are early or mid-career? What skills or things should they focus on if they want to move into the AI ML space?
Yeah, so it's a great question because I have 2 college kids and I share the same thing with them. So I'm sharing the secret with all of you here, the stuff I taught to my kids. And I will say 3 things here. One is the math side. Sorry if nerds, happen to like math. and math, I think math is a foundation for a lot of stuff you do, and analytics, right? I mean, the way to become analytical mind, that's actually important. And then the second one is the business acumen. It's the impact. It's more than just a mathematician. It's the impact you're looking for. Why do you do these things? The why. A lot of people don't ask the question why. They end up just doing whatever they're doing, right? So that's important in terms of skill set. And then the third one is communication, which is super important. And you need to be able to communicate your ideas with others, because a lot of people, my preference, I like doers, because the magicians we have, most of them are doers. They get the work done. But I wish they could talk more, a little bit more. But the opposite is probably worse, because if people, I've seen people who can only talk but can't do anything. That's probably worse. But on the other hand, communication is important. So the analytical capability, business acumen, and communication. These 3, I think, would be greatly important.
Wonderful. Well, we're out of time. This has been incredible advice, really insightful. Thank you so much for being here.
So, Daniel, I really enjoyed the conversation, and you have a great show here, and thank you for inviting me here.
That was Dr. Wei Li, Intel's Vice President and General Manager for Artificial Intelligence and Analytics. And thank you to Mouser for sponsoring this episode of Moore's Lobby. If you enjoy this podcast, make sure you are subscribed in your favorite podcast tool, and it would really help us out if you'd share this episode on social. So go check out the Moore's Lobby and All About Circuit social media pages and share the post with this episode in it. Thank you for joining me today in the lobby. I'm Daniel Bogdanoff, and I'll be right back here in 2 weeks with a whole panel of folks. It's going to be a really good one.